Welcome again, everybody, for this second session of the Bandoleros. For this second talk, I have the pleasure to introduce Jo-Kyung Kim from University of North Carolina, and he will talk about compactification of the moduli space of minimal instantons on the Fano threefold V4.
Okay, great. So I would like to thank the organizers for the opportunity to talk. So I will talk about the compactification of moduli space of instantons on V4. So let me start with sort of recalling the classification of Fano threefolds of index 2 and Picard rank 1. So the definition of a Fano variety, I believe everybody knows. So a smooth projective variety is Fano if the anti-canonical divisor is ample. And we call the index of V to be the largest integer one can find, so that the anti-canonical bundle is R times H for a ample divisor H. So now let's take V to be a Fano threefold with Picard group isomorphic to the group of integers, and we will denote the ample generator by H. And then we'll call the let's fix the index of V to be 2. Then the degree we'll call the degree of V by D. That's defined just to be the triple intersection of the ample generator. And then there is this classification where we know that D will have to be one of the 5 integers, so from 1 to 5. And then, well, in each case, there's a concrete description. So if D equal to 5, then V is the Grassmannian GR25 using its Pluko embedding into P9 and then cut by a codimension 3 linear section. And if D equal to 4, then V4 is the intersection of 2 quadrics in P5. So smooth quadrics. And in fact, this V4 will be the type of variety that we're going to focus on today. Now, let me finish the classification. If D equal to 3, then V3 is just a cubic threefold in V4, in P4. And then if D equal to 2, V2 is a double cover. Sorry, the 3 got moved around. So is a double cover of the projective space ramified in a quartic. And D equal to 1, then V is just a degree 6 hyperplane in a weighted projective space. Okay. So now before I move on, I would like to also say one word about the topology of these varieties. So the even degree singular cohomology of V4 are all isomorphic to the group of integers. In fact, this is true for all degrees. So this is for I equal to 0, 1, 2, 3. And it also holds true for the degree from 1, 2, 3, 4, 5. Right. So, and they're generated by classes of just V4 itself, hyperplane, a line, and a point, respectively, for each of the I. All right. So now I would like to move on to introduce what's called the associated curve. Let me call it C to this V4. So recall that V4 is the intersection of 2 smooth quadrics. So just these 2 quadrics, then we'll give a pencil of quadrics. So this is a P1 worth of it. And then if you denote the homogeneous coordinate by X and Y, then XY just go to XQ1 plus YQ2. Right. So then if you just look at the discriminant locus, so then we can easily see that there are 6 degenerate quadrics on this pencil. And by our assumption that the intersection of Q1 and Q2 is smooth, then we can check that these 6 points are actually distinct. So we'll just let C be the double cover of the P1 ramified in the 6 points. And as I said, since the 6 points are distinct, so then C is a smooth projective curve. And by Riemann-Horowitz, we can easily check this is a genus 2 curve. Okay. So now this shows how we can construct this genus 2 curve out of this threefold V4. Now there's another way to understand the relation between these two things. So let me put it in a remark. So this is going from the other direction. So V4 can be realized as moduli space of stable vector bundles of rank 2 and a fixed determinant of odd degree on the curve C. Okay, and since the determinant is odd degree, so this will turn out to be a fine moduli space. So we will denote the universal family by capital S for further use. All right, so this completes my quick introduction to the threefolds. So any questions at this point? All right, great. So now I would like to go on to quickly recall the derived category of V4. Right, so I'll start with sort of some generality on just the derived category of Fano threefolds of index 2. So if we let V be any threefold as above, index 2 and Picard rank 1, so then if we look at the collection of this two line bundles, so OV and OV of H is what's known as an exceptional collection. So essentially, this is just to say there's very nice cohomology vanishings between between the home and X of these two line bundles. And once we have this exceptional collection, this will in turn provides a what's known as a semi-orthogonal decomposition of the derived category of V. So it goes as follows. So well, there will be two components just corresponding to these two line bundles, O and OH. And then we can take what's called the right orthogonal of these two, this exceptional collection, and usually they're denoted by Ku of V. So this is known as usually called the Kuznetsov component. Right. And usually lots of the geometry of V is reflected in this Kuznetsov component. So now let me specialize to the degree 4 cases. And so, and recall the following theorem. So this is, I believe, due to Bondel and Orloff. So the Fourier-Mukai functor. So to identify a Fourier-Mukai functor, you just need to give its kernel. In this case, we will use the capital S that we have just written about the universal family. So that will provide a Fourier-Mukai functor from the derived category of C to the derived category of V4. And this, in fact, provides an equivalence of the derived category of C onto the Kuznetsov component of V4. So we can just view V4 as a copy of the derived category of the associated curve inside this threefold. Okay. And this is sort of the main theme of this talk. So we'll use sort of derived category techniques to try to understand the sheaves on this Fano threefold V4. Okay. All right. So now for the third part, I would like to start a quick introduction to instanton bundles on threefolds. many of you are experts in this, so I welcome any comments and corrections. Right. So the story of instanton models, I believe, started with the paper of Atiyah, Dreamfield, Hitching, and Manning, where they investigated young Mills instantons on the fourth sphere. Right. And then, so the sort of more mathematically defined instanton bundle started on the projective space P3. And they're defined in the following way. So they're stable vector bundles, which I call E, with rank of E equal to 2, C1 of E equal to 0, or C2 of E greater than or equal to 1, and such that they satisfy the following cohomology vanishing conditions. So the first cohomology of E twisted by -2 is 0. And this is usually called the instantonic vanishing condition. Okay, so I would like to just remark that the C2 is usually called the charge of the instanton. And this twisting in the instanton vanishing condition, this -2 should be think of as half of the canonical bundle on P3, sorry. All right. So instanton bundles have been heavily investigated, and one of the main theorem to understand it is what's known as the monad construction. So let me recall that. Okay, so monad construction just says every instanton bundle of charge n on P3 is the middle cohomology of the following complex. So you have n copies of O -1, and then it injects into 2n plus 2 copies of O, and then it subjects onto n copies of O1. All right, so this theorem was initially proved, I believe, using classical algebraic geometry techniques, but I would like to sketch a quick proof of it using derived category. So recall there is the important result of Bennington, in which he proved that essentially there is a semi-orthogonal decomposition of the derived category of P3 in the following way. So you start with O -1, and then O, O1, and O2. Okay. So if we look at this complex that we are shooting for in the inside the theorem of the monad construction, and we can see that it only involves the first 3 terms. So now this leads us to the following proof. So the first thing we want to do is to show that basically E lies inside the first the component that's formed by the first 3 terms. So essentially, this is to say it lies inside the right orthogonal of O2, and this is in turn is just equivalent to showing that all cohomologies of E twisted by -2 is 0. So and we have seen that the instantonic vanishing condition in the definition already provides 1 degree, and all the others basically follows from the stability of the bundle and also the stereoduality. All right. Now, secondly, so after this step, we have basically established that our E will lie inside the component formed by the first 3 terms, and then we can just use since we know all the trend classes, so then we just compute E on each component, and we will readily get how many copies we need and this form of complex. All right, so I hope this this quick sketch just show you that the idea of derived category can be useful in understanding the instanton bundles on 3-fold. Okay. And then not only are the bundles themselves the torsion-free generalizations, of instanton bundles have also been heavily studied. So I'd like to just mention some names, but I'm sure I'll have to miss many. So Mariam and Troutman, and then Jardine and Gargett and Jardine in the several papers. And so one result I would like to specifically say is, so in the paper of Jardine, Markushevich, and Tikhomirov, so they show that when the charge equal to 1, i.e. the minimal charge, then the moduli of instanton bundles of this charge can be compactified by what's known as, so they're torsion-free generalizations, I would call them instanton sheaves. That's only singular on curves of degree equal to 1. So the singularity, the singularity of a torsion-free sheaf is just the support of its difference, of the difference between the sheaf itself and to its double due. All right. So now I would like to move on to the notion of instanton bundles on Fano threefolds of index 2. Okay. So let me start with the definition. So this definition is due to Vanzi and Kuznetsov. Although the version I'm presenting, I believe, comes from Kuznetsov's paper. So let X be a Fano threefold of index 2, and assume the Picard group of X is isomorphic to group of integers. So essentially the type that we started with the introduction. So an instanton bundle is a stable vector bundle E with, essentially we're just copying down everything from the Picard P3 case, but making some necessary changes. So rank equal to 2, C1 of E equal to 0, C2 of E, in this case, it will have to be greater than or equal to 2. This is some cohomological computation check. And then we require that H1 of over X of E twisted by -1 is 0. Since in this case, the index go from 4 to 2 now. So the twisting is just -1. Okay. So this is a definition of instanton bundles on Fano threefolds. So now I'd like to just say that from now on, we will we'll only focus on instanton bundles of minimal charge. On instanton bundles of minimal charge, i.e. the case when C2 is equal to 2, and we will omit the word minimal. So from now on, any mention of an instanton bundle, we're talking about minimal instanton bundles. Okay. All right. So maybe, are there any questions at this point? Okay. So now I would like to also in the next remark connect my topic to some of the other topic in this conference. So on V4, one can easily check that the instanton bundles, again, let me in this case emphasize of minimal charge, they're in one-to-one correspondence to stable Ulrich bundles of rank 2. And in fact, this correspondence is just twisting by the input generator. So how do you know that? So basically, E go to E twisted by 1. So at the end, we will arrive at a smooth compactification for the moduli space of instanton bundles of minimal charge. And so that will turn out also to be a nice compactification for the stable Woodley bundles of rank 2 on V4. Okay. So now we would like to move on to the investigation of the moduli space. So I would like to start with a result of Kuznetsov. So Kuznetsov showed that instanton bundles on V4 are in one-to-one correspondence to stable vector bundles of rank 2 and degree equal to 0 on the associated curve C. And well, I should mention there is some extra condition that these rank 2 bundles, vector bundles, need to satisfy. So, and the technique you use to establish this result is using the derived category. Okay. So now, on the other hand, if one only cares about the compactification, so there's an obvious compact or projective moduli space that contains the moduli space of instanton bundles. So the moduli of instanton bundles is an open subscheme of the moduli space of semi-stable sheaves of rank equal to 2, C1 equal to 0, C2 equal to 2, and C3 equal to 0 on the V4. So essentially what we did was, if we go back to the definition here, we just relax a bunch of stuff. So the stable goes to semi-stable. Vector bundle, we relax it to sheaves. Now we filled in the C3 just because, well, it should be 0 because of we're looking at generalizations of vector bundles, and we kind of omit the instantonic vanishing condition. So the good thing about looking at this moduli space is just by the classical theory of Simpson, so this will turn out to be a projective, hence compact. But it might not be the nicest compactification we want because, well, it can be, we do not know if it's connected or irreducible or smooth. Right, but this moduli space will turn out to be the sort of the center of topic for the rest of this talk. So let me just fix some notation. So from now on, I will denote.
Excuse me, can I ask a question? So
is
this identification just as sets or as schemes? So is it just the one you mentioned by Kuznetsov?
It's in fact in terms of schemes, but well, one have to be a little bit careful to check. This extra condition does it sort of so this instanton bundle will be so its image will be an open subscheme inside a big moduli space, but one have to be a little bit more careful. So that's why I only stated one correspondence.
Sure, thanks a lot. Sorry.
So I have a question as well, just to clarify this result by Kuznetsov. One thing you just said, the extra conditions are open conditions in this moduli space.
Yes.
And in this statement, you're also including the minimality of the instantons on V4.
Yeah. So from now, everything is minimal.
Okay. So do you know, does Kuznetsov say something about what happens if you consider other charges?
Yes, absolutely. So Kuznetsov's result was actually about all minimal charges. So all charges, I'm sorry.
All charges, okay.
Yeah, but yeah, I'm only citing sort of the minimal case.
Okay, thank you very much.
Yeah, thanks. Okay, and now, as I said, I would like, since I do not want to write this kind of a long condition on the sheaves that we're looking at over and over again, I'll just call them instant sheaves. Okay, so the referee of my paper was kind enough to point out this is not actually the right notion to use, but just for the sake of this talk, we'll be a little bit careless and just use this quick sort of shorthand notation. Okay, so now I'd like to draw a picture to illustrate maybe the relation between these two moduli spaces. So we start with this threefold, and then there is this curve. All right. So on the threefold, we have the moduli space, which I'll denote by m_inst. So again, it's just defined to be the semi-stable, the moduli space of semi-stable sheaves with rank 2, C10, C22, and C30 on V4. And over on the curve, we'll be looking at the moduli space of semi-stable vector bundles with rank equal to 2 and degree equal to 0. Right. And so inside both moduli space, so we have this stable locus. And then inside the stable locus, there is this open subscheme that's representing, instanton bundles. And by Kuznetsov result, this can be mapped one-to-one to an open subset to the moduli space on the curve. And now it's a good time for me to really specify how this morphism goes. So we use the Fourier-Mukai functor, take its left adjoint, and then plus a shift by -1. So this functor will induce a morphism between these two open subscheme. Okay, so we have this two moduli space, and we are able to use the so this functor to identify open part of them. All right, and so now let me also remark that one reason for us to really care about one sort of motivation for us to make use of the moduli space on the right, so this semi-stable rank 2 degree 0 vector bundles on C, this moduli space is well understood. So it's due to a paper by Raman and Narasimhan, and they show that this is a smooth projective variety of dimension 5. And in fact, it's a P3 bundle over the Jacobian of C. Right, so this is as nice of a variety as one can hope for. Okay, and we'll try to understand the relation between these two moduli spaces. All right, so the starting point will be, let's start looking at the strictly semi-stable locus of C, of the moduli space over C. So the pointing here correspond to S equivalence clauses of the direct sum of two line bundles, where each line bundle is degree 0, so lies in the Jacobian. All right, so we would like to see if there are anything for the moduli space on the threefold that sort of correspond to these type of points. Of course, inside the strictly semi-stable locus. And in fact, that will turn out to be the case. So so the object we're interested in this case are ideal sheaf of lines. So if we take let L denote the line, then one can easily check the following two facts. So one is the ideal sheaf of this line is a stable sheaf. That's trivial from the definition. And the second one is the trend character of any instanton bundle you take is twice the trend character of an ideal sheaf of line. So for any instanton bundle E. Okay. So this will lead to the following observation. So the extension of two ideal sheaf of lines are strictly semi-stable insta sheaves. Right. And to further connect this from the moduli space on the right. So again, I'll cite a result of Kuznetsov, in which he proved that there exists an isomorphism from the Fano variety of lines on V4 to the Jacobian of this associated curve C, and given by none other than just the functor that we have seen before. So the left orthogonal of phi applied to IL and then twisted at -1. All right. So after these, well, we can see that at least inside the strictly semi-stable locus, we will have points that correspond to S equivalent classes of IL1 plus IL2. And then it will be mapped sort of in a one-to-one fashion by the same functor to the points on the modular space over C. Of course, there's a case, there's also the issue of S equivalence, but since we're using a functor on like an exact functor from the derived categories, so the S equivalent class will be sort of trivially preserved. All right, but it still remains to understand, well, are there anything else inside the strictly semi-stable locus, and what are the things that lies in the middle? So to answer these questions, we'll need to get a full classification of the insta-sheaves on V4. So are there any questions at this point?
Yes, please. The two lines can be the same?
Yeah, so there's no restriction on it on the two lines.
Can you get something like a double line? Is that?
No, I don't think so.
Some of the ideal sheaves of two lines, you get the. Yeah. Okay. So the lines can be anything. Okay. Thank you.
Right. So again, this is sort of corresponding to on the side of the curve, you can have any two line models and take the either extensions. Right. Okay. Great. So now let's move on to the classification of insta sheaves on V4. All right. So the main inspiration for this part is the work of Joel in 2000, in which he classified instanton sheaves on cubic threefolds. And recall, it's just in our classification, this was what's called a V3. So the degree 3 cases of these type of threefolds. And through some computations and checking that, we can extend this result to V4. And it gives the following classification. So let E be an instanton sheaf on V4. Again, it's just a semi-stable sheaf satisfying the Trin classes requirement. So then it falls into the three categories. So if E is stable, then either E is locally free, or E is associated to a conic, which we'll call Y in V4, such that we have this short exact sequence. So E is the kernel of two copies of the structure sheaf into the theta character of the conic twisted by 1. So let me write down where theta is the theta characteristic of Y. So let me just quickly explain. So a conic is just a curve that's isomorphic to P1 and of degree 2 using this embedding. And the theta characteristic is just, a line model such that its square is the canonical bundle on Y. So in this case, P1. So the theta character of a conic will just be the negative of the ample generator of the Picard group. And since it's degree 2, so twisting by 1 of the theta character will just give a ample generator. It's just the ample generator of the Picard group of Y. It's all a bit awkward since it's a degree 2 thing, so referring to the ample generator is kind of hard. All right. Now, on the other hand, if E is strictly semi-stable, we have seen that E can be the ideal extension of two ideal sheaf of lines. And in fact, that will turn out to be the only case. Of lines It will be have to be the ideal sheaf of lines in V4. Okay, so this gives the full classification of the semi-stable sheaves that fits into the Chern classes that we're looking at. And the good thing is, well, for all the non-locally free cases, well, we have a very concrete construction on which we can perform computations. And I would like to also remark that the non-locally free instanton sheaves are they're singular. So again, the difference between these sheaves and their double locus, double dual, they're supported on curves of degree, again, less than or equal to the charge. So in this case, less than or equal to the minimal charge 2. Of course, this result is to be compared with the result that I mentioned of Jardine, Markushevich, and Tikhomirov. Okay.
So it's not always pure.
No.
Okay.
Right. And I would like to also mention a technical lemma. So remember in the definition of instanton bundles, there was this instantonic vanishing condition. And in fact, it holds for all these type of sheaves. So if E is an insta sheaf on V4, then H1 of E twisted by -1 is 0. So the proof of this is a little bit technical. So I'll just sort of give a sketch. So first one, identify that the H1 can only be 0 or one-dimensional. And if it's one-dimensional, one can cook up actually a curve that's a smooth curve that's pushing the limit of the degree and genus relation, and then go from there to build a contradiction out of it. Okay, so that's all I'm going to say about the proof of this lemma. All right. So are there any other
in the statement of the theorem, the conic Y, it's a smooth conic.
Ah, yes. Thank you very much.
That's what you mean.
Yeah, this is extremely important. Thanks. I sort of missed that. So it had to be a smooth conic. Yes, absolutely.
So something like reduced conic or a double conic doesn't happen.
No, it wouldn't work.
Okay.
Yeah. Well, I'm not sure which condition it will break. Probably the stability, I think. Right.
Okay, thank you.
Okay. Yeah. All right. So now I'd like to move on to wrong color. Now I would like to use this classification to consider the relation of instanton sheaves to vector bundles on the curve C, associated curve. So let me begin with this easy lemma. So let E be an instanton sheaf on V4. Then thinking of E as an object in the derived category, it actually lies inside the Kuznetsov component. All right, so a quick sketch of the proof. So this is just equivalent to showing that E lies inside the right orthogonal of these two line models. So I'll alternatively use O1 to denote the OH, where H is sample generator. And this is again equivalent to just some cohomology vanishing. So E twisted by -1 and E itself, so all cohomology will vanish. And this follows from the classification of this class of sheaves, plus the technical lemma, then plus the stability and Serre duality. So essentially using a combination of these four, we can easily arrive at these cohomology vanishings. Okay, and I would like to also mention that the vector bundle case was already, of this situation was already proved in Kuznetsov's original paper. Okay. So now let's recall one more time that we had this Fourier-Mackay functor that established the equivalence between the derived category of C to the Kuznetsov component of V4. So this inspires us to maybe consider, well, what will the sheaf look like in the derived category of C? Right. So the following theorem answers this question. So let E be an instanton sheaf on V4. And then we'll denote F to be this functor that we have seen several times applied to E. So the left adjoint of phi applied to E shifts by -1. Then this is a semi-stable vector bundle of rank F equal to 2 and the degree of F equal to 0. So essentially, it says this functor we have used initially only on the instanton bundles sort of extends to the whole moduli space. And moreover, well, the stability is preserved in the sense that stable sheaf will go to a stable vector bundle on C, and strictly semi-stable will go to a strictly semi-stable one. And S equivalency is also preserved. And again, this is just due to the fact that we're using a exact functor. All right. So now let me redraw the picture we had. So over here I have the M-inst, and over here I have the, on C I have the degree 0 rank 2 vector bundles. So initially we only had this identification for the open subscheme that's started with instanton bundles, and it go to its image over here. And then we show that, well, there's this identification also extends to the strictly semi-stable locus. And this theorem, new theorem now we're saying, says there is a morphism that extends all these green and purple parts, and that's using the exact same functor to the whole moduli space, M-inst. So we'll denote this morphism by little phi. Okay. And as I said, this little phi already sort of induce bijections on both the green and purple part. So it's natural for us to suspect, well, maybe it's isomorphism, or at least some morphism satisfying nice property. So to prove this, we need to understand just a little bit more about this M-inst moduli space. So the following proposition says the following, says that M-inst is smooth. And it's actually a smooth scheme of dimension 5. So a quick sketch of the proof. So for stable points, one just compute the x2 of EE and show it vanishes. So it indicates it's smooth at this point. So this is just due to the fact that after you apply the functor, E will correspond to a sheaf on the curve. And sort of the cohomological dimension of the curve is 1, so we cannot have any non-trivial x2. And then one compute the x1 of EE and show it's 5-dimensional. And then for the strictly semi-stable locus, this is a little bit more involved. So basically use some GIT analysis and make use of Luna et al. Slice here. But similar arguments has already been done in a paper of Laszlo and also in Zhuao's original paper. All right. So now, after this proposition, we can state the main theorem. And it just says this morphism, new morphism phi from, now let me write down all the numerics. So the semi-stable vector, semi-stable sheaves of rank 2, C1 equal to 0, C2, 2, and C3, 0 on V4. From this to the modular space on C of semi-stable degree 0 rank 2 bundles is an isomorphism. All right. So, and as we said at the beginning of this talk, the moduli space over C is a P3 bundle over the Jacobian of C. So it's a smooth projective variety of dimension 5. So, and then in turn, this moduli space of instanton sheaves is also a smooth projective of dimension 5 connected. And it also contains the moduli space of instanton bundles as an open dense subscheme. So this is as nice of a compactification as one could hope for. All right, so let me give a quick sketch of the proof of the main theorem. So the key ingredient for the proof is the risky main theorem. And so the version of this theorem I use is that a morphism that is bijective, birational, and proper will have to be an isomorphism. All right, so since both moduli spaces are known to be projective, so the properness is trivial. So for the bijectivity, so injectivity follows from the fact that we're using a sort of a equivalence of derived categories. So the functor that induces this morphism. And then along with the fact that both sides are smooth and dimension 5, we can easily get the surjectivity. Now to show the map is birational, we can show that the stable locus inside the moduli space of instanton sheaves is actually embedded as an open subscheme into the moduli space on the curve by phi. And to show this, one can just check the tangent space of stable locus are mapped bijectively, and then plus the fact that this is the morphism is injective, and it will lead to open embedding. All right, so that's a quick sketch of the proof of the main theorem. So are there any questions? All right. So great. In the remaining time, I would like to report also a similar result on the degree 5 case. So let me draw one.
Excuse me.
Yeah.
But you know that both are smooth of dimension 5?
Right.
Or is it part of the proof?
Well, the fact that the moduli space over C is smooth of dimension 5 is proved in Ramanan and Narasimha's original paper. And we prove that the moduli space on the left is smooth smooth of dimension 5 using this proposition.
Okay, so it's enough to show bijective then to prove isomorphism.
Right. Well, along with a little bit other technically, but yes, essentially it's a bijectiveness.
Okay, thank you.
Yeah. Okay. Now, as I said, I would like to use the remaining time to report a similar result on V5. So let's quickly recall that V5 is the codimension 3 linear section of GR25. Inside is Proco embedding to P9. And let me also mention that the derived category of V5, in this case, it will have a semi-orthogonal decomposition that comes from a full exceptional collection. So the first two terms I will explain later, and then the last two terms are just O and O1, as we have seen in the general case. So this Q is the restriction of the tautological bundle from the Grassmannian, and this Q is the quotient bundle. And the star denotes a dual, so we're using U and Q dual inside this exceptional collection. And the component that's formed by U and Q dual is what's known as the Kuznetsov component in this case. And by computing the Holmes between U and Q dual, we can see that the Kuznetsov component is actually equivalent to the derived category of representations of the Kronecker quiver with 2 vertices and 3 arrows. So I'll denote this by K sub 3. Right. Excuse me. And then, so we'll perform sort of a similar analysis as the sort of previous part of the talk. So in this case, we have insta sheaves E on V5. So the first thing we show is it emits a following sort of resolution. So you have 2 copies of U injects into 2 copies of Q dual. and then the co-kernel will be E. I'm writing it in this way just to show that, well, this part all lies inside the Kuznetsov component. So using this and trying to connect this to the quiver, we can see that this instanton sheaf will correspond to a representation of a quiver, a key sub 3 with dimension vector 2 and 2 over each of the vertex. And the key thing is we can show that this is in fact a semi-stable representation. And also all semi-stable representations will come from such a construction. And then finally, let me state the main theorem in this case. So the moduli space of semi-stable sheaves is rank 2, C10, C22, and C30 on V5 has a connected component which is isomorphic to the moduli space of semi-stable representations of K sub the Kronecker quiver with 3 arrows and of dimension vector 2, 2. Also, this moduli space is well known, well understood, is actually isomorphic to P5. And this P5, this component will contain the moduli space of instanton bundles, minimal instanton bundles, as an open dense subset. This is also a very nice compactification for the moduli space of instanton bundles. All right, so you may ask why in this case you need to talk about the connected component instead of the whole thing. So this is due to recall the technical lemma that we had in the middle of the talk. So I was not able to establish that for the degree 5 case, essentially due to numerical reasons. All right, so that's all I would like to talk about. So I think I'll stop here, and thank you very much for your attention.
Thank you very much. So any question?
So in the technical lemma,
yes,
how I thought the vanishing was part of the definition of instanton?
No, so let me go back to here where I started using this notation. So in this one, I put no condition on the cohomology. So it's just semi-stable sheaf satisfying the Chern character condition. So that's in fact, so this this technical lemma is actually something non-trivial to show.
Okay, so the lemma says that for any sheaf which is semi-stable with that C2, you have this vanishing.
Yes.
Okay. And that's not true for the V5.
So my conjecture is it holds true for the V5, but I just could not prove it.
Okay.
Yeah.
So you don't know of any other component, do you?
Yeah, I've no. I have no example of a contra example.
I see. So, sorry. One other question. So can you do this for higher rank?
Sorry, you mean higher rank? I mean,
for you know, if you remove the rank 2 assumption from your sheaves,
right,
and keep the orthogonality condition, then you also have some map to the derived curve.
Right. I honestly I haven't attempted. I'm not. So I guess I was not exactly sure. So what was the correct condition to impose on, like, restriction to impose on those sheaves? But yeah, I think that's a very interesting question. But I don't know at this point.
Okay.
Right.
So I have a question as well.
Yeah.
So you said that the moduli of bundles on the curve has a projection to the Jacobian of the curve with fibers being free.
Right.
Do you know what this projection onto the Jacobian does in terms of the bundles on V4?
I think it essentially is just mapping to the determinant of that bundle. So we are only requiring it to be degree 0, so it can vary. So the determinant can vary inside the Jacobian.
No, yeah, but in terms of the original instanton sheaf. So start with a instanton sheaf. How do you produce?
Right, that's a great question, and I attempted that, but I was not able to construct any relations. So sorry, my answer is again I don't know.
Okay, yeah. Good, thank you.
Right.
Alexander has a question as well.
I think, may I ask such a question? I remember that there was some work of Giangiacomo Sanna about the moduli of instantons on V5, probably of the minimal charge. Do you remember that work? I remember Sanna was a student of Kuznetsov in some 10 years ago, probably.
Yes, absolutely. So in fact, my paper made actually several use of results in Sanna's paper.
I see.
Yeah, I'm aware of his result, and I believe his result is a little bit different from mine. But yeah, so I guess he did not make use of I guess the relation to the representations. But
yes,
yeah,
right. He did not.
Yeah, but I'm aware of his result, and his result was actually quite useful in my paper. Yeah.
Okay, thank you. Thank you.
Yeah, thank you.
Okay, so may I ask, like, if you can clarify just the quiver interpretation in the first case of V4?
Sorry, I think quiver is only used in V5 case.
Okay. So in the case of V4, there is no interpretation as a quiver variety?
No. So in
okay.
that case, we'll have to go to the associated curve C.
Okay. So thank you. Are there any other questions?
Maybe a silly comment or question. So to prove this isomorphism for V4 and the curve C, is it possible maybe to use an infinitesimal technique, like showing that the two tangent obstruction theories are the same or related? Like if you show isomorphism on tangent spaces and injection on obstructions, I think you would be done even without knowing smoothness of the left-hand side.
Yeah, maybe. I'm not very good at the infinitesimal arguments, but yeah, I think maybe that can also be done. Yes.
I thought about, because you need to have pretty good control on the tangents and obstructions. So
right. So we had great control over the stable locus, but yeah, might be a little bit tricky on the strictly semi-stable ones.
Oh, that's a good point. Yes, you're right.
Yeah.
Thank you.
Yeah.
Okay. So thank you. And let's thank the speaker. So we will resume in